All right. Hi, everyone. Before the lesson starts, I just want to quickly go over where the notebook file is for everybody. So I have it open here, but I'm going to go back to Files and Home. So you can see where it is. So it's in Workshop, in Lessons, and then it's in 04_materials_API. And we're going to be working on the MAPI lesson empty. So you can click that and you should see this notebook. If anybody's having trouble finding it, you can type in Slack. I think we have a couple more minutes till we start. So we will wait for everyone to get back. Hey, everyone. Just one last time before we start, just in case anybody missed it, I just want to show again where this notebook is. So if you go back to Home, it's in Workshop, in Lessons, and you're going to click on 04_materials_API. And the lesson we are going to be working out of is the MAPI lesson empty. It should look like this. Okay, well, it is 2:20, so let's get started. So my name is Jason Munro. I'm a materials project staff member here at Berkeley Lab. And I've been given the opportunity to talk to you guys about the materials project API, or the MAPI, as you might hear some people refer to it as. So our API is really the go-to interface for accessing large amounts of materials project data. And so today I'm going to talk about the new materials project API that we've been working on for a while, alongside the new website that you got to see this morning. In fact, the API is actually what the website uses in the backend to pull data that it displays on the materials details pages. So you'll get to interact with it. So in this lesson, we're going to go over a description of the API and how it's structured and what the data looks like. We're going to go over getting an API key that you need to access the data. And then we're going to go over using our Python client that we've written to actually access data. And we're going to go through a couple of interesting examples to show how it might be useful. Okay, so let's begin. So the first thing I'd like everyone to do is just run this first cell here. This is going to do a couple of things. It's going to suppress warnings for us. And it's also going to define a convenience function called shortlist, which just is going to allow us to print long lists in a sort of very specific way that's a bit nicer. So I will point out that within CoCalc, we have already installed the package that you will need. However, if you want to run these notebooks locally using Jupyter, you will have to install this mp-api package. It is pip installable, and so you can do that, but there's no need to do that right now. So we should already have access. Okay, so the first step is to make sure everybody has their API key. And to do that, we need to log into the new Materials Project website. And so you can do that by clicking this link here to get to nextgen.materialsproject.org. And then all you need to do is click the API button in the top right. And if you scroll down, you'll see this box in the middle where it says your API key. And you can click the button to log in if you're not already logged in. So I'm going to do that. And I'm going to continue with Google. And if you do that, you should see your API key here. So please keep this to yourself. So obviously you can see mine, but I will be resetting it after this. But please do not share this with anyone else. So you can go ahead and copy that. So I'm going to do that, copy. And then I'm going to go back to the notebook. Now, there are a couple ways to make sure that the client that we're going to be using knows about your API key. So the first is with an environment variable that you can set. And the second is just by explicitly giving it the API key. We are going to opt for the latter just because it's easier in CoCalc to do it that way. However, the filled notebook explicitly has the environment variable that you would set if you wanted to do it the other way. And so you can take a look at that if you wish. So I'm going to go ahead and I'm going to paste my API key here as a string and set it equal to this mp_API_key variable. I'm going to press Shift Enter to run that. And so now we can just reference mp-API key, and that should point us directly to our API key. Okay, so the Materials Project API is organized into a bunch of different endpoints. And each of these endpoints provides access to different types of data. And so I list all of the endpoints here. This is actually a screenshot from a page I will go to in a second. But some of the more important endpoints, for example, are materials. And this contains all of the core materials data that we use to define what our materials are. There's also endpoints like thermo, which contains all of our thermodynamic data. A very, very important endpoint is summary. And we're going to take a look at this a bit later, but this allows us to access aggregated data across a lot of these different endpoints and query over many different types of material properties. And so all of this information can actually be found on the API details page. And so you can click this link here in the in the notebook, and it should take you back to the page that we were just on. So this page has a lot of really great information on how to use the API and the client. It has a nice tutorial. If you scroll down, you'll see this is the list of endpoints that I showed. If you keep going, there's lots of additional information. And we're going to cover a lot of what's contained in here, but this should be one of the first places you go if you're having trouble outside of the lesson. For those that are a bit more familiar with APIs, there is more detailed documentation on all of the endpoints. And so you can find that by going back to the notebook and by clicking more detailed documentation. And that should take you to this docs page. So there's a general description, but if you scroll down, there are a list of all of the endpoints with sub-URLs, descriptions of the data that's associated with them. And if you click, you can see a bunch of the parameters that you can use to query data. I'm not going to go over this in great detail because a lot of this, for those for the vast majority of users who will just be using our client, they don't have to worry about this, but I just want to point out that this is there for those that are a bit more experienced. Okay, so I'm going to close all of these windows and go back to the notebook. And another thing I want to say is that, so our API is a REST API. I'm not going to talk about what REST is in great detail, but what you should know is that REST is a standardized protocol that allows different computer systems to communicate with one another efficiently. It's quite popular. And in these types of systems, there is information or data that's organized into what we call resources. And then each of those resources is uniquely identified with this URI, this uniform resource identifier. And in the case of our API, these are just HTTP URLs, which everyone is very familiar with. And so because our API is a RESTful system, we can interact with it with REST requests. And so to actually get data, what we can do is make a what's called a GET HTTP request with our API key to a specific URL that is associated with one of our endpoints. And so I show an example of how you might make a direct request like that with the Python requests library. So this code should already be in there for you. And so you can see here, we are making a GET request, and we are using this URL. So this refers to our API, so api.materialsproject.org. So we are sending the request to the materials endpoint. This refers to the fact that we are trying to get data for MP149, which is silicon, just ground state silicon. And then there are a couple of HTTP variables, which in this case define the information that we are after. So we're after the material ID, even though we already know it in this case, and the structure. And so if we send a GET request to this URL and we provide our API key within the header of the request, if we run this, you should see that it returns this data. And I will also paste it up below so you can compare. And so this data is a JSON document. So for those that are at the primer, you have seen JSON before. It stands for JavaScript Object Notation. And you'll notice that this looks, for those that are less familiar, this looks exactly like a Python dictionary. And it's this mapping that's going to let us easily work with this data using Python. So, this is great. And you can make these types of requests to any REST API that exists out there, but this is quite tedious. You can imagine that if we wanted to query over lots of complex data, that you might have to construct some convoluted URL every time, and that would be no good. So instead, what we've done is we have written a Python client that constructs all of these requests for you, and you interact with it through a set of methods. And so that makes it a lot easier to access materials project data. So we're going to start by using that client. So it is called the MP Rester. And we are going to first import it and create an instance of it. So to import it, we can type from mp_API dot mapproj import MP Rester, and the MPR are capitalized. So I'm just going to press enter a couple times. Actually, I'm going to run that, and I'm going to insert a cell below. Okay, so now we just need to instantiate it. And you can instantiate it the same way that you've been instantiating lots of other objects. So we can do something like this, for example. We can type MPR equals MP Rester. And this is very important. We have to tell it what our API key is. So I'm going to pass it this MP_API_key variable that we set earlier. And so if I run this, we now have an instance of MP Rester. So I'm just going to insert a cell above here. And so we can do things with it now. And so, for example, I'm going to use it to show what the available parameters are associated with the materials endpoint. And so this is very useful as it allows us to see all of the available fields that are associated with a specific endpoint. And so if I run this, you can see with the materials endpoint, which is an attribute of MP Rester, we have this available field attribute, which gives us all of these values. So things like elements and sites, composition, chemsys, volume. So this is very useful. So although you can instantiate it this way, we actually recommend that you use the with context manager to ensure that sessions are properly closed. And to do that, all we have to do is type with, and then MP Rester again. And once again, we have to make sure to remember to pass it our MP API key. So we type with MP Rester as MPR, enter. And then we can do the same sort of thing. So in this case, I'm going to print MPR dot, but instead of the materials endpoint, I'm going to look at the available fields for the thermo endpoint. So we're going to do mpr.thermo.available fields. If I press Shift Enter, you can see we have a bunch of fields printed. So things like energy per atom, formation energy per atom, energy above Hall, that sort of stuff. Okay, so I mentioned that interacting with the MP Rester mainly consists of interacting with a bunch of convenience methods that we've written. And so we're going to go through a couple of examples of using those methods. And these are generally written to tackle common tasks that people have with the API. And so the first one we're going to take a look at is get band structure by material ID. So this, just like the name suggests, allows us to get a band structure object, which we can then plot. So if you run this first cell that I've already written for you, this will set up a function that will allow us to plot the band structure with the BS plotter object within PyMetGen. So I won't go over this, but you can take a look at that. And so we're going to use the MP Rester's get band structure by material ID method to get the data for a specific material and plot it. So let's do that. So I'm going to type with MP Rester, MP_API key as MPR. So we're going to type this a lot. And I'm going to type band structure equals MPR dot get band structure by material ID. And we need to pass it an MP ID. And so I think above it says MP123, but I'm actually going to do MP149, which is silicon. I'm going to press Shift Enter to run that. I'm going to insert a cell above here. And then I'm going to call our plot underscore band structure function and pass it BS. And if we run that, we should see a band structure plot for silicon. So as another example, there is a convenience method for getting material IDs for different formulas or chemical systems. So let's take a look at that. So I'm going to do the same thing with MP rester MP API key as MPR. Okay, so I'm going to type L equals MPR dot get materials IDs. And then I'm going to pass it a chemical formula. And so let's pass it LIFEP04. I'm going to run that. I'm going to create a couple of cells. And I'm going to pass this output to shortlist so we can take a look at it. And so you can see it's returned a list of MPIDs that are 70 items in length, and we're just truncating that and showing the first 5 items. And so, for example, we can also use this same convenience method to get data for a chemical system. So I'm going to go back. I'm going to just edit this. And instead of passing a chemical formula, I'm going to pass it Li-Fe-P-O. Run that, shift enter, and then I'm going to shift enter the next one as well. And you can see, oh, there are 388 MPIDs, and it's printed out a couple of them here. Okay, so there are many convenience methods. And so I'm going to show you how you might be able to, or if you want to take a look at all of the ones that were available, how you might do that. And so I'm going to type with MP rester key again as MPR. And then I'm going to type MPR dot and press tab. And so you can see if I scroll down, there are a ton of different methods we can call. So things like get structures, get structure by material ID, get material IDs, which we just used, get entries, get DOS by material ID, lots of stuff. And so I am going to scroll down, and we're going to use a couple more with a small example. So we're going to use the get structure by material ID method and the get substrates method to try and get some substrates that we might want to use to grow this material, the calcium titanate 327. Okay, so let's do that. So I'm going to type with MP rester API key as MPR. And I'm going to first get the structure with the get structure by material ID method. So structure equals MPR dot get underscore structure. Now I'm going to autocomplete here with tab. So if you press tab, you'll see this menu pops up and you can click the get structure by material ID method. So you don't have to type the whole thing out. And I'm going to pass it the MPID for this material, which is 4163. And then I'm not going to run this yet. I'm just going to press enter to go down a line. And now I'm going to get the substrates. So substrates equals MPR dot get underscore. And again, I'm going to type get underscore sub, press tab, and it will autocomplete to get substrates. And I'm going to pass it the same MPID. And then I'm going to press enter a couple more times. And I'm going to print both of these things. So I'm going to print the structure just to make sure that we are looking at the right material. And then I'm going to print this. So substrates is actually going to be a dictionary. And in order to get the chemical formula for the different substrates that it's suggesting, we can access the subform key of that. And so I'm going to construct in list inline in this way. So I'm accessing the subform key for the S document in substrates, and I'm making a list out of that, and then I'm printing it. So if we run that, you can see, okay, great. So this looks like the correct structure for calcium titanate 327. And if you scroll down, you can see a list of chemical formulas that correspond to substrates that we might want to try to use. Okay, so at this point, we've used some convenience methods, so you should be comfortable with first finding documentation if you need it, instantiating MP Rester, and also using some of the methods. One thing I do want to show before I move on is I'm going to insert a cell below here. If at any point you want to read more into what these different methods do, you can use the same procedure that you've been exposed to thus far. So you can use the help function, or you can use the question mark feature. And so I'll show you what that looks like, for example. So with MP Rester, so I'm going to type npr.get structure by material ID. And I'm going to, in this case, press Shift Tab, which should pop up this introspection. And you can see here's the doc string for this method. So get a structure corresponding to a material ID. We need to pass it a material ID. There are some optional arguments here, which we didn't use. And it returns a PyMetGen structure object or a list of structure objects if these other options are passed. So you can do this for any of the methods that that you can see or that you saw before with when we tab completed. Okay, so I think I'm going to move on to section 5. So there are lots of methods for doing individual tasks, but by far the most powerful method is the query method. And what this allows us to do is search over aggregated data for material in the database. And so you can search over data that might be associated with different endpoints. So you might use this, for example, if you wanted to filter materials according to its stability using energy information from thermo, or in addition to elasticity data. So you would use this method to do that. So let's construct some queries just to see how it works. So first, we're going to query for SiO2 compounds in a couple of different ways through ChemSys formula. So to do that, I'm going to type with MP Rester as NPR. And I'm going to type results equals npr.query. And then I'm going to pass ChemSys formula as SiO2. And I'm going to print the length of this length results. Okay. So if we run that, this might take a second. You can see there are 320 results. And so we can do the same thing with chemical system, just as an example. So I'm going to type the same thing, results equals npr.query, but instead I'm going to pass it an SiO chemical system, and same thing. So it should just take a second. Okay, so we have 342 entries. So let's investigate what results actually looks like. And so to do that, I'm just going to fill in this line here. So I'm just going to pass results where these underscores are. And for the second one, I'm going to access the first element of this. So I'm cheating a bit because I know this is a list. But if we run this, you can see results are returned as a list, as I said, of class emit core summary doc. So the query method returns a list of summary doc objects, and we can access data for different materials from that object. And so we can do that in a couple different ways. We can access the data directly as an attribute or as keys within a Python dictionary. And so first, before we do that, I'm going to insert a cell here, and I'm going to print what one of these docs looks like. So I'm going to print the first element of results. And you can see it contains a lot of data. So you can see there's a structure in here, but there's lots of other data and sites. Looks like there's some XAS data in here, K-point, tons of stuff. So let's access just a couple of fields from this. So let's first do it as an attribute. So I'm going to set doc equals results 0. And I'm going to first access the material ID within this document. And so to do that, we just need to type dot material ID to treat it as an attribute. And then I'm going to print that. And you can see, great. So it's picked out the material ID from this large data document. So I'm going to go back to the cell, and I'm going to do the same thing with another piece of data. So let's do it with the structure. So doc.structure now. And I'm going to print that as well. And if we do that, you can see, great. OK, it's obtained the structure. OK, so just to show that we can also do this, we can do this as a dictionary. I'm going to set doc equal to results 0. And we need to convert this to a dictionary first from this summary doc object. We can do that with the dict method. And then I'm going to access the same data, but using keys of the dictionary. So material ID equals doc, and then material underscore ID. And we're going to print that. And great, we're able to access it in the same way. And if you don't believe me, we can do the same thing with structure. So I'll just do this quickly, doc structure, and we'll print structure. And you can see, great, same thing. Okay. So as another illustration, I want to show that for ChemSys formula, which is very useful and will probably you will probably make use of quite a bit. We can also use wildcard characters. And so you saw this a bit with the website, but let's use that functionality to find all AB03 compounds within the materials project. So with MP rester, MP API key as MPR. And then I'm going to type results equals, and then MPR.query. And now I'm going to pass ChemSys formula as star 03. So you've probably noticed, or I guess I pointed this out, but if I scroll up, there's a lot of data in this data document, the summary doc that we obtained before. And so we don't necessarily need all this data. And so now let's tell the query method, oh, we don't actually require all of that. Just give us, the things that we need. And so the way we do that is by passing fields as a list of things we're interested in. And so in this case, I'm going to pass material ID because I'm interested in that. I'm also going to pass formula pretty because I want the chemical formula. And let's also obtain the structure. And so if we run that, this should take a second. So you get this nice bar to show, oh, okay, looks like there are 2,541 matches. And so now I'm going to print some of the results. So results, I'm going to pass results to shortlist. And if I scroll up, actually, that is not what I wanted to do. Okay, let's try that again. So let's go down to section 8, and I'm going to insert a cell above here. I'm actually just going to print results 0. And so you can see, okay, it looks like there is a structure. But now if you look at all these extra entries, you'll see that they are all none, except for material ID, which is hidden here. And so we've only obtained the data that we need. Okay. So you also might be asking the question, how do I find all of the fields that are contained in this document easily without just pulling data? And so one way to do that is with that get available fields attribute that I showed earlier for materials and thermal. And so I will demonstrate that now. So I'm going to insert another cell here. And MP rester has MPR. But now we just have to take a look at the summary attribute. Get available fields. Oops. Try that again. Oops, it is not get available fields, excuse me, it is available fields. There we go. Oh, and I didn't print it, so let me print that quickly. Okay, great. And so you can see here, here's a list of all of the fields that should be contained within the document that you have at your disposal to query on. And just one other way to look at these, we can also, actually, I'm going to reuse the cell. We can also call the query method and press Shift Tab and look at the doc string. And so you can see down here, we get a list of all of the things that we can pass to query on. So material IDs, volume, density, crystal system, space group number. There's lots and lots and lots of things. As I said, this allows you to query over a bunch of aggregated data. And if you keep scrolling, you can see descriptions for all of these. So this is another very useful place to look if you're stuck or having trouble. Okay, so let's move on to section 6. So as I mentioned, query method lets us search through aggregated data, but this is only some aggregated data. This is not everything. And so in order to query all of our available data for a particular category of data, we can use search methods that are specific to individual endpoints. And so as an example to show this, let's query for initial structures for all cubic materials with 2 or less atomic sites using the materials specific search method. And so by initial structures here, what I mean are structures that we start from to actually run our calculations. Okay, so to do that, I'm going to type with MP rester, MP API key, same as always, as MPR, colon. Going to type results equals mpr dot materials, because we're interested in data specific to the materials endpoint. And I'm going to call the search material docs method. And so in the same way that we looked at the query method, we can press Shift Tab to look at what options we have. And so you can see there's a lot of the same information. So crystal system, space group number, that was also in our query method. But in this case, we would not be able to obtain these initial structures from the query method. We'd have to look at the material specific data for that. And so what we're looking to do is find, so we're looking for cubic materials, and we know that we want ones with 2 or less atomic sites. And so I can see in these options, we can maybe use crystal system. So that's great to search for cubic materials. And there's N sites as well. So perfect. Okay, so I'm going to pass crystal system as cubic. And I also want to pass something for N sites. One thing I didn't actually show you was, or point out, I should say, is that next to the variable here, we can see what it's expecting. And so in this case, it's expecting a tuple with 2 integers. And so if we're confused by this, we can also scroll all the way down to the doc string and read the description for N sites. And so you can see here, minimum and maximum number of sites to consider. Okay, great. We know that should be 0 and 2 in our case. So N sites equals 0, 2 as a tuple. And by default, this method will, just like the query method, give us documents that have everything possible populated. But in this case, we aren't interested in all of that data. So I'm going to, just like before, pass a value for fields. So a list of values of things that we actually want. And I'm going to type material ID. And we know we also want initial structures. And that's it. So with this method, it turns out we actually also have to pass all fields equals false. I'm just going to make this a little easier to read. And you can see that here. So if we were interested in figuring out how to only return specific data, that information is also in the doc string here. Okay, so I am going to run that. Shift enter. Okay, my shift enter is not working. There we go. And so again, I'm going to take a look at what this data is. So results, and then results. And I'm going to access the first element just to see what the type is. I'm going to close this so that we can see. Okay. And so we can see, okay, so it's giving us a list of, in this case, these are materials doc objects. And so each endpoint, as you can guess, will return a specific doc object that will contain the data. And so much like summary doc, we can access data through its attributes or by converting it to a Python dictionary. And so let's do that. So we know we're looking for a material ID. So maybe let's print the material ID for the first document returned. So results 0 dot material ID. Okay, great. And let's do the same underneath for the initial structures. Okay, great. And so you can see here, this is a list of structures. In this case, there's only one entry. Oh, actually, no, sorry. There are two structures in here, my mistake. And these are the initial structures associated with this material. Okay, so looks like we have some more time, which is good. So what I'd like to do now is move on to the exercises, because I think trying out some of these methods is really the best way to figure out how to use them. And so what I'm going to do is give everybody a bit of time to try and work through exercise 1, and then we're going to take a look at it. So to find exercise 1, we can click Files in the top left, and it should take you back to the Materials API folder. And you can click on MAPI exercise 1. So I'll point out that the solutions are already are in here as well. So if we don't get to finish everything, you can always go back and look at the solutions. Okay, so I will give everybody maybe 5 minutes to take a look at this and start working on it, and then I will come back and go through it. Okay, so let's start working through this exercise. I'm not sure we'll be able to get to the second one, but maybe I can just go over it quickly before we leave, but we'll see. Okay, so first I need to put my API key in here. So before we were passing that MP API key variable to MP rester, but I'm just going to paste my API key directly in here. Okay, so let's use the API to get the symmetry property for all SiO2 compounds. And so I have a hint here that describes how to do it. So this should be mpr.query. And we're going to use chemsys formula again. And pass SiO2. And we know we're only interested in the symmetry property. So I'm going to pass fields equals, and then a list with symmetry. Okay. So let's run that. You might get this warning, which is fine. Okay, great. So I'm going to insert a cell above here, and I'm going to just look at the length of the data that's returned. So SiO2 underscore entries, just to make sure we have data. Okay, great. There are 320 entries in this list. So now let's extract the crystal system property for the entries that we've retrieved and put them into a list. So you'll see I have this crystal systems list, and we're looping through all of the entries in SiO2 entries. And we're appending something from each of those entries to crystal systems. And so yes, that's right. And so I give a hint here that crystal system is a subentry of symmetry. And so we can get that by typing entry.symmetry.crystal system. So we can run that, and I'm just going to insert another cell above here. And I'm going to print a subset of this list. So print crystal underscore systems. And we're going to print the first, 10 entries. Great. And so you'll see, okay, it looks like this was successful. So we've extracted all of the crystal systems for these entries. So hexagonal, rhombic, cubic. And if you're interested in figuring out the material IDs for these materials, for example, you could go back and pass material ID as part of fields and also print that here, obtain structures, whatever you need. Okay, so let's process the data and let's create a plot from it. So we currently have a list of crystal systems. And so now what we'd like to do is create a dictionary, count dict, where each key is the name of a crystal system. And the value is how many times it appears in this list. And so we can do that here. So I'm going to iterate through each entry of crystal systems. So for entry in crystal systems. And what I'm going to do is, so I think in the solutions, I have an inline solution, but I'm going to be a bit more verbose here. So I'm going to say if entry in count dict, which means it's just checking to see if the key is already in that dictionary. I'm going to say count dict equals 0, or excuse me, not equals 0, plus equals 1. And I'm going to say, oops, else. So if it's not in, then we know it does not have a key for that crystal system, and I'm going to set it equal to 0. Okay. So we can run this, and Let me see what's going on. Type int is not iterable. I forgot to actually pass entry here. Is counted as dictionary? Okay, great. And so now hopefully, so I have some code here before to actually plot this data. And so if everything is correct, we can run this and we should get a plot that shows us the count of all of the crystal systems in the data that we obtained. Okay, so there is a second exercise, but I'm not sure we have enough time to go through everything. So I might leave it there and ask if anybody has any extra questions, and I will help answer them. And if for anyone interested in taking a look at that exercise, they can go and look at the notebook that's in the same place. So I'll go and I'll show that again in files. It is this exercise 2, and it's a bit more involved. So it's an example that uses the query method among some other PyMetGen features to screen the materials project for materials that have a negative Poisson ratio. So this is a really, really nice sort of mock research example that was put together by John Dagdalen. I highly recommend taking a look and trying it out. The full solutions are also in the same folder. Yeah, this is really great. So with that, I think I will leave it there a bit early. And if anybody has any questions, I will take a look at Slack and at CoCalc, and please ask, and we will help get it sorted. So thank you.